So now let's take a look at some definitions. We're going to actually define two different types of improper integrals, and they'll be related to the integrals that we know and love from Calc 1. Remember that in Calc 1, we technically had to have two conditions in play in order to be able to integrate a function like this. One of those conditions was that a and b would be used to describe a closed interval, right? That is, I had an interval from a to b that I was integrating on. We also had to have that f of x was continuous on the interval from a to b. These were the requirements of a Calc 1 integral. And what we're going to see here is that if I begin to break these individual rules, I am going to create different types of what we call improper integrals. In the example above, you'll notice that we broke this first condition because while we had a clear starting point to our red space, we didn't have a clear stopping point. And so this created what we would refer to as a type 1 improper integral. If I break that second condition, I'll create what we call a type 2 improper integral, which we'll cover in a later video. So let's take a look here at the type 1 improper integrals and see exactly what we mean by them and how exactly we represent them. So I start us off with this. Suppose that I have a function and the integral from a to t exists for every number t that for t greater than or equal to a. So again, kind of like the picture that I have or had up above, if I had a curve and I wanted to find the area under it, and I can find the area from a to t pretty easily, then as long as I can keep pulling t to the right side and always creating a green area that I can find, then we'll say the following. We'll define some new notation, an integral from a to infinity. When we write this, what we really mean is that we're going to be doing a limit as t moves to infinity of an integral from a to t f of x dx. Of course, again, provided that this limit exists. Now, I can say the same sort of thing if I could imagine reversing the picture. What if I had my value of b existing over here, and maybe I had a curve kind of going the other way? If I could find the area all the way out until a value of t, and I can continue to find this area every time I slide t a little bit lower, then I can define an improper integral that would be negative infinity to b dx, and I'll just define that as a limit. Here t would be going towards negative infinity, right? I got to slide t down, and I would just apply that to the integral that goes from t to b f of x dx. Of course, this is again provided that the limit actually exists, and I get an answer here. Now, I can also kind of combine these two types of integrals together to get something that goes from negative infinity to positive infinity. But let's see how that works down below. First, before we get there, I'll go ahead and define some other pieces of terminology. I'll say that if these integrals here are actually going to exist, then they are going to be called convergent. So these integrals are called convergent if their corresponding limits exist. So that is, if I calculate the limits that we have up here and I actually get a number back. I can then also say that if this limit does not exist, remember that includes positive or negative infinity, then these integrals are called divergent. So we're just going to have some names that allow us to quickly communicate whether I ultimately have a finite amount of area under a curve, convergent, or an infinite or undeterminable amount of area under a curve, which would be called divergent. So you'll see that I'm going to use that term immediately in the next definition. If it's the case that an integral from a to infinity and an integral from negative infinity to a are convergent, that is, they both represent some amount of finite area, I can imagine that maybe looking like this in a picture. Suppose that a is right here. If I can say that the area from a off to infinity is going to be convergent, and the area from negative infinity up to a is convergent, they both have finite amounts, then we will define the following. We will define, switch colors back here. So we will then go ahead and define an integral from negative infinity to infinity of our function, and that will actually just be equal to the sum of those two integrals. That is, I could take like the green integral, add on the blue integral, and I would have all the area under the curve. This should even be fairly reminiscent of a property of integrals that you talked about in Calc 1, where you could kind of integrate from any starting point, stop in the middle, and then kind of continue the trip onwards. Here, we're just pausing at some value of a. It's important to note, though, a down below can be any number. It doesn't actually matter what a is. It can be any real number that we choose. So we could choose it as a 0 or a 10 or a pi. It doesn't matter. We can make that choice on our own. So these are what we would refer to as type 1 improper integrals. And in the next couple videos, we'll take a look at how exactly we can go ahead and work with trying to evaluate different improper integrals of this first type using these definitions that we established here.